Alright, welcome back. In this video, we're going to go over differential equations, how to set them up, how to verify solutions, how to solve them, and slope fields. Differential equations happen all the time in nature and physics. That's why calculus was invented, is to describe natural phenomena. Differential equations are basically the language of nature. And when we're setting up differential equations, we're going to be given a scenario here in words, and we're going to change the keywords into a mathematical language. So whenever we see the word rate, we're going to represent that by a differential or a derivative, a rate of change. So like a derivative dn over dt. Most of our rates are going to be with respect to time. So it's going to have dt at the bottom. If something says directly proportional or directly varies, such as a rate being proportional or directly varies to some number, then we're going to have the rate on one side, and to write a direct proportion, it's k times whatever the variable is, in this case n. So if we're talking about a rate is directly proportional to some specific number, we're going to have k times n. K is going to be some constant, but we're just going to write it as a k. If it's inversely proportional, then, or inversely varies, then we're going to write the rate equals k divided by n. And if we see the word jointly proportional or jointly varies to two variables, that's what a joint variation is, basically linear to two variables, then we're going to have k times m times n. So I'm going to go through, like I said, you only have to do the odds here. I'll go through the odds, help you get these set up and solved, but you're responsible to know how to do these. Number one says the rate of change for growth of a bacteria in a petri dish is directly proportional to the number n of bacteria in the dish. So most of the times I tell you what the variable is here. It's n. Up here it's saying that the rate of change, so we're going to represent that by a differential dn with respect to time dt. Then it says directly proportional, so that means we're going to have some constant k times our number n. So that's it. You're just setting these up. You're not solving them or anything else. You're just writing a differential equation that's going to represent this scenario. Number three says the proportion P of the population who has seen a viral video increases at a rate proportional to the proportion of the population who has not yet seen the viral video. So here we have the rate who has seen it increases at a rate proportional, so here we're talking about dp, so it's going to be dp dt. That's the rate that the proportion is going to increase, and we're told that that varies directly to those who have not seen it. So think about it this way: if 40% or 0.4 have seen it, who has not seen it yet, that's going to be 1 minus p. So this represents the people who have not seen it yet. So think of p here like a decimal. If 20% have seen it, then 80% have not, and we just take that away from 1. And there we go. There's our setup. Number 5, the rate of growth for a population of field mice is inversely proportional to the square root of the number of mice. So this is just going to be dm dt. That represents the rate of change of the mice over time. And we're told that that varies inversely, so it's going to be k over something. K over what? The square root of the number of mice. And so that's it. Okay. Number 7, the rate of decay for a substance is inversely proportional to the amount of material left. So this is kind of similar to the viral video one. So for number 7, here we have the rate dA dt, and inversely proportional would be k over the amount. But since it's going to be a negative rate, we want to put a minus sign here because it's going to be going down. So if we have a rate of decay, that means that the rate has to be negative here. The rate of velocity is slowing by 9.8. At the same time, the rate at which velocity v is changing is proportional to its velocity. So number 9, we have dv dt, And it is slowing down, so it's going to be a negative 9.8. And at the same time, the rate at which the velocity is changing, and it is directly proportional to its velocity. So we're going to have k times v for that one. So this represents the slowing down, and it is also proportional to the original velocity. Number 11, the rate at which y changes with respect to y varies directly to the sum of y and x. So the rate of change at which y changes, dy dt, it says with respect to x, varies directly to the sum of y and x. So we're going to write it like that. And this would be dy dx in that case. And the rate at which y changes with respect to x, so that's going to give us dy dx, is inversely proportional to the difference of y and x. And it also says it varies directly to y, so y is going to go on top in this case. So here we have a combined variation. It varies inversely to the difference and directly to y. So that's simply how you do the front. Let's go on to the next page. All right, starting with number 15, now we have to verify that we have a solution to a differential equation. So differential equations, sometimes they're set up in this notation with the y primes. Sometimes they're set up in the Leibniz notation with the dy dx's. Both of these mean the rate, or the derivative. Here we're saying that the derivative of some function is equal to x cubed. We want to verify that this is going to be a solution up here. So first thing we want to do is to take the derivative of what we think is our solution. So if we're given that this is a possible solution, what would be the derivative of this guy? Well, we take the derivative of x to the fourth divided by 4. We would use the power rule. So we bring the 4 out in front, drop it down a power, divided by 4. The derivative of negative 6 would be 0. And so that's going to come out to x cubed. And that is the derivative. So we have y prime is equal to x cubed. That's what we have here. And what does this say? It says y prime is equal to x cubed. And so it checks out. That's all you have to do for that one, is to make sure that the derivative is actually x cubed. Here we're saying that the derivative is equal to 5 times y. So here we want to take the derivative, and this time I'm going to write it as dy dx, taking the derivative of this function with respect to x. It's an exponential, so we're going to have 3e to the 5x. Got to do the chain rule, so if it's exponential, the derivative is e to the u times du. So u here is 5x, so we're going to multiply by 5. That's going to give us 15e to the 5x. So there is our derivative. Now we're going to go back and plug this back in, because here it's a little bit different. So on the left side here, we have 15e to the 5x. On the right side, we have 5 times y. But what are we told that y is? Now we look here and we see that y is equal to 3e to the 5x. And if we multiply out the right side, we get the same thing. So that's how we verify it. Here we have to take the derivative, plug it back in, and also plug in the original solution that we have, the y. We're going to plug in 3e to the 5x in for y here. So we're not actually solving this, we're just showing that we have a solution. Okay, 19 now gets a little bit more complicated, because now we have a differential equation that has both x and y in it. And we want to verify that this is a solution. So we want to be taking the derivative of it, putting it on the left side, and then we're going to take this function and plug it in for y here. So when we take the derivative here, we probably want to rewrite this as 4 plus x squared to the 1/2. And now we can take the derivative of that. Now we can use the chain rule. So the 1/2 is going to come out in front. We have 4 plus x squared. We're going to drop it down a power, so it's going to go to the negative 1/2 times the derivative of the inside, which is going to be 2x. And we want to simplify this, so the 2 and the half here would cancel out. So we're going to have x times 4 plus x squared to the negative 1/2, which is the same as x over the square root of 4 plus x squared. So this is what we're going to put in for the left side here. So we have x over the square root of 4 plus x squared equals, now we read off what the right side says. So the right side says that we have x on top, x is just a variable, and then we have y on the bottom, but y is this original function. So we plug that in, 4 plus x squared. So here's our x, here's our y, here is the derivative, and we can see that the derivative is equal to x over y. So it's true. 21, verify that y equals 2e to the x minus 1 is a solution here. And here we have y prime is equal to x plus y. So start by taking the derivative of what we think is our solution. What's the derivative of 2e to the x? It's going to be 2e to the x minus x. So the derivative of that is just minus 1. The derivative of negative 1 is 0. So now we have the derivative. We put that on the left side. And then we are going to copy down the right side. So that's x plus y. What is y? Y is this whole thing. So plug that in, 2e to the x minus 1. Simplify. So these would cancel, and we get the same thing on the left side and the right side. So we verified that this is a solution. Okay, starting with number 23. Now we are going to actually solve differential equations and get our own solutions. And so to do this, we want to get all the y's and dy's on one side and all the x's and dx's on the other side. These are called separable because we can separate the x stuff and the y stuff. So we have separable differential equations. There's whole courses on differential equations and other types of differential equations that you might take. So this is just the starting point. There's a lot of differential equations that we're not going to get into, but we're going to do these easy ones. And we're going to separate them, and then we're going to integrate both sides because we're going to have differentials on both sides. We can integrate both sides to get rid of the differentials. Typically, we would have plus c's on both sides, but we're only going to put the plus c on one side. This is going to give us the general solution. So it's a general solution because we're going to have this plus c. Later on, we're going to have particular solutions where it's going to give us some initial conditions that are going to allow us to find whatever the value of c is. So here's our first equation. dy dx is equal to 2x plus 4. So we're going to treat the left side like it actually is a division problem, even though it's a differential. We're going to split up the differentials. And I've got to multiply both sides basically by dx. And you can see that the right side here, all it has is x's. So I don't have to do anything to the right side. I'm going to multiply the dx over there with it. So we have dy is equal to 2x plus 4 dx. And that's going to allow us to integrate both sides. So we're going to integrate this side with respect to y, and that's going to give us y. And we're going to integrate this side with respect to x. So 2x, bump it up the power. Now it's x squared divided by 2. But we're dividing by, multiplying by 2, divided by 2, so the 2's would cancel. And then we're going to have 4x here. And don't forget, what else do we need? We need the plus c. So here is our equation. And we can go back and check. We can verify the solution. If we take the derivative of this guy, we do get 2x plus 4, which is what this says. And again, we need to have the plus c here because we're talking about any equation that looks like this would be a solution. So it's a whole family of curves here that we're talking about. Any of these quadratics that look like x squared plus 4x. And this could be 2, this could be negative 4, whatever c we want here. Okay, so we're starting out with some easy ones here. 25, another easy one. Separate. So we got to write it as dy equals 4x minus 2 dx. Integrate both sides. What do we get on the left side? We get y. What do we get on the right side? This is going to be 2x squared minus 2. And again, don't forget the plus c. Usually we would have to put plus c's on both sides, but we want to move all the c's together and just call it one big C over here. So there's our answer for 25. Okay, 27 looks like this. dy over dx is equal to 1 over x to the 4. So again, we want to put the x's together. So we're going to have dy is equal to 1 over x to the 4, but maybe we write that as x to negative 4 dx. So we want to write it as a power rule. And now we can integrate both sides, integrate the left side, integrate the right side. This side is going to give us just y. Up here, we're going to bump it up a power, so it's going to go to x to negative 3. And then we're going to have to divide by negative 3, add c to it, and we've got our solution. Okay, 29, we have dy dx is equal to 1 over x. Okay, first thing I want you to do is to separate the dy's and the dx's. So we're going to write this as dy is equal to 1 over x dx. You know the drill, integrate both sides. On the left, we get y. On the right, what is the integral of 1 over x? It's going to be natural log of the absolute value of x. And again, don't forget the plus c. (31) dy dx is equal to 2 sine of x. So we're going to split up our integral here. dy is equal to 2 sine x dx. Integrate both sides. Left side we get a y. Right side, take the integral of 2 sine of x. That's going to give us negative 2 cosine of x plus c. (33) dy dx is equal to negative cosine of x. Split up the differential. Integrate both sides. On the left, we're going to get y. On the right, the antiderivative of negative cosine is going to be negative sine of x. Okay, 35. Again, the right side here just has x's, so we're going to move the dx over on that side. We want to probably rewrite this, so we're going to write it as negative 2, and then x minus 1 raised to negative 2 dx. We're going to integrate both sides here. And integrating the right side here, you might want to make a u substitution, unless you can see what the integral is going to be. So we can say u equals x minus 1, then du is going to be equal to dx. So we can rewrite this integral as negative 2 u to the negative 2 du, and take the antiderivative, integrate it. We're going to have negative 2, and then we're going to bump this up. So it's going to bump up to a negative 1 with a u in it. So that's x minus 1 divided by negative 1. So that's going to change that to a positive. So we're going to end up with 2x minus 1 to the negative 1 plus c, which we could write as 2 over x minus 1 plus c. (37) dy equals 2 over x plus 3 dx. Integrate. On the left we have y. On the right it is basically 1 over x, or 1 over x plus 3. So you should recognize that this is going to be 2 natural log absolute value of x plus 3. You can do u substitution. U is equal to x plus 3. And then we have our plus c. Okay, so far we've been finding general solutions. Now we're going to find particular solutions that are going to satisfy the initial condition. So here is our original differential equation. Here is our initial condition. We're going to solve it first. So get it set up. Negative 2x plus 3 dx. So we're going to take our differential equation, separate it, integrate it. We get y is equal to negative x squared plus 3. And now we're going to use what it tells us here for our initial condition. This means that 3 is going to be our input and 1 is going to be our output. So this is going to go in for x, and this is the y value that we get out of it. We're saying y of 3, or f of 3, is equal to 1 here. So when we put a 3 in for x, we should be getting 1 here. Because when we normally solve these, we get a plus c here at the end. So this is going to help us to find out what c is. So for 39, we're going to put the 1 in here for y, for 1. 1 goes in for y. And negative 3 is going to go in here for x. I forgot, this is 3x here. So 3 times 3 plus c. 1 equals, simplify this. This is negative 9. This is positive 9. These would cancel out. So we have 1 is equal to c. And then once we have the c value, we're going to go back to this and plug it in. So our particular solution here is not negative x squared plus 3x plus c, but y equals negative x squared plus 3x plus 1, because we just found that c is equal to 1. Okay, 41. dy over dx is equal to negative 2 over x cubed, and then this is our initial condition. So let's first set up and solve the differential equation. So we're going to have dy is equal to negative 2x to negative 3. We're going to rewrite it so we can use the power rule. We're going to integrate both sides. This is going to give us y. On this side, we're going to bump it up a power, so it's going to go to x negative 2, which we're going to divide by negative 2. So the negative 2's would cancel. So it looks like we're just going to have y is equal to x to negative 2 plus c. And now we're going to plug in our initial condition. So we're going to plug 2 in for x, and we're going to get negative 11 fourths. So now we're going to find, so let's put this in a box so we look at that later. Now we put in negative 11 fourths for y. We're going to put in 2 for x. Remember, this means 1 over x squared plus c. And we got to find the value for c here. So we got to solve this. This is going to come out to 1/4. So we're going to subtract 1/4 here from both sides. And negative 11 fourths minus 1/4 is going to be negative 12 fourths, which is going to be negative 3. So we have c is equal to negative 3, which now we can write our final solution, which is y equals x to negative 2 minus 3. So we go back to this guy, and now that we know the value of c, we can plug that in. All right, 43. Let's get this set up. So dy equals negative 2 sine of x dx. Integrate both sides. Here we get y. On the right side, what is the antiderivative of cosine? Sine is going to be cosine, negative cosine, and so that's going to come out to a positive 2 plus c. And we want to figure out now what the c is. So we're going to put in 5 pi over 6 into this guy. And for y here, we're getting negative square root of 3 minus 1. 2 cosine of 5 pi over 6 plus c. And then we have to look up on the unit circle, what is cosine of 5 pi over 6? Cosine of 5 pi over 6, you can check, is going to be negative square root of 3 over 2 plus c. Here the 2's would cancel, and that's going to give us negative square root of 3 minus 1 equals negative square root of 3 plus c. So it should be pretty easy to see that c is going to be negative 1. So we've got now to plug that back in. So now that we know what c is, we can plug it back into here, and we have y equals 2 cosine of x minus 1 for our particular solution. Okay, 45, set up, separate. Dy equals 3 over x dx. integrate, integrate. Here we get y. Here we get 3 natural log of x, absolute value of x, plus c. We're going to plug in 2. And this is going to go in for y. So 3 natural log of 2 minus 3 equals 3 natural log of 2 plus c. So here, the 3 natural logs of 2 is going to cancel out. And we get c is equal to negative 3. And we put that back in for c. So our solution is going to be 3 natural log absolute value of x minus 3. Because that's the value of c that we found. Alright, starting with 47. Now we're going to go back to solving some more general solutions for differential equations. This time, though, they look a little bit different because we have equations that involve both x and y. And again, our strategy is going to be the same. We want to get all the y's together with the dy's and all the x's together with the dx's and integrate both sides. And eventually we're going to have to solve for y here. So this is simply going to work by, in this case, just multiplying both sides by y squared. It's kind of like just cross multiplying here. So we're going to end up with y squared dy equals x squared dx. So cross multiply y squared times dy, x squared times dx. Now we can integrate both sides here. And now we got some interesting stuff going on here on the left side as well, because this is going to be y cubed over 3. And we could put plus c here, but remember the plus c is going to end up with x's anyways. So let's just go to this side, and we're going to have x cubed over 3 plus c. When you're solving these, you have to keep track of where is your c's here. Sometimes when you're solving more complicated differential equations, you might have multiple c's as well, and then you have to add little subscripts to these guys. But we're not quite done yet because we still want to solve this guy for y and not y cubed over 3. So we're going to multiply both sides here by 3 and then take the cube root. So we're going to have y cubed is equal to 3 times this, x cubed. And we could put plus 3c here, but c times 3 is just going to be another c. Okay, so this c is different than this c, but it's still going to be a constant. And so we're not going to put 3c here. And now we're going to take the cube root. So we just end up with y equals the cube root of x cubed plus c. 49, separate it. So we're going to get y squared dy equals 2e to the x dx. Integrate both sides. Here we get y cubed over 3. Here we're going to get to this is exponential, so it's just e to the x times 2 plus c. Important to put your plus c here at this point, because if you don't, you could mess up the solution. So when you're integrating this guy, put the plus c right away before you start solving it for y. And now we're going to solve this for y. Again, we're going to multiply both sides by 3 and take the cube root. So we're going to end up with y equals the cube root. 3 times that is going to be 6e to the x. 3 times c is still going to be a c. So we have our answer. Y is equal to the cube root of 6e to the x plus c. Here it looks a little bit different. We got 2xe to the y. So again, we have to look at the x part and the y part, and we want to get all the y's together and all the x's together. So maybe I'll do this in a couple steps here. We're going to multiply both sides by dx first to give me this. But this is a function with a y in it, so we need to move that to the other side. So we basically need to divide both sides by e to the y so that this side will cancel, and we end up with 2x dx. Over here, since I have 1 over e to the y, I'm going to write it as e to the negative y dy. Now we got them separated. All the y's and dy's on the left, all the x's and dx's on the right. So we can now integrate. Integrating the left with respect to y, it is e to the negative y, e to the u, du, so it's going to be negative out in front, plus c, but we're going to put the plus c's over here with the x's. Integrate this guy, we're going to have x squared plus c. And now we have to solve this guy. So let's get rid of the minus sign first. We have e to the negative y equals negative x squared. And c times the negative, we're still going to write that as plus c, because we don't know if c here is positive or negative. C times something else is still going to be a c. And now we have to do the inverse operation of the exponential. So this is e to the negative y. So we're going to take the natural log of both sides. So this is going to give us just negative y equals the natural log of negative x squared plus c. And then lastly, multiply both sides by negative 1. So we're going to have y equals negative natural log of negative x squared plus c. Okay, 53. dy dx is equal to 2x over e to the 2y. Separate both sides. We're going to have e to the 2y dy equals 2x dx. Integrate both sides. Integrating this side, this is e to the u, so it's still going to be e to the u divided by u here, which is going to be 1/2. And then on this side, we're going to have x squared over 2, so the 2's would cancel. Put our plus c there. Then we want to get rid of the 1/2 next, so what do we have to do? We're going to multiply both sides by 2. So that's going to give us e to the 2y equals 2x squared plus c. And just like the previous one, when we have e to a power, and we want to get this y here, we're going to take the natural log of both sides. So take the natural log of the left, take the natural log of everything on the right. That's going to give us 2y equals natural log of 2x squared plus c. And then divide everything by 2, or we could just put the 1/2 out in front. Okay, 55. Here we have dy over dx is equal to e to the x minus y. So this way is a little bit tricky because the x and the y are both exponents, or they're in the exponents of the e here. So the first thing we want to do is property of exponents to get these guys split apart. We could write this as, well, one way to write it is just e to the x over e to the y, like that. That's probably the easiest way to write it, because when we're subtracting exponents, that's the same as dividing these guys. Dividing two things that have the same base means we subtract the exponents, so we can go the other way and write it as e to the x over e to the y. So property of exponents used there to change this, so we can write it as e to the x over e to the y. And now we just have e to the y dy equals e to the x dx. Integrate both sides. This is going to be e to the y plus c. This is going to be e to the x plus c. And we're going to take the natural log then of both sides to get the y by itself. Y equals natural log of e to the x plus c. 57. dy dx is equal to 1 over cosine y. Split up. We got cosine y. dy equals 1 dx. Integrate. Integrate. The integral of cosine is sine of y. The integral of 1 is just x plus c. And now we want to get the y here by itself, but it's inside of a sine. So how do we do that? What is the inverse operation of sine? Is going to be inverse sine. So we're going to take the inverse sine of both sides here. That's going to give us y on the left and inverse sine of x plus c on the right. Okay, 59. Here we have dy dx is equal to 4y sine of x. And I want to get all the y's to the left side. So everything here is being multiplied. This is 4 times a y times the sine of x. I want to keep the 4 and the sine of x on the right side and just divide by y on the right. And I can write that as 1 over y dy equals 4 sine of x dx. Integrate, integrate. This is going to be natural log of y. And over here, the antiderivative integral of sine is going to be a negative cosine, and don't forget the 4 there, of x plus c. And now I want to get still y by itself. Here, though, the y is inside a logarithm, a natural log. And how are we going to undo that? Well, we're going to exponentiate both sides. So e to this power is just going to give us y back because the e and the natural log are inverses of each other. So it's going to return back the y. And here we're going to have e to the negative 4 cosine of x plus c. All of this is going to be the exponent of the exponential here of e. The answer key has this written a little bit differently. They're going to have, because we can split this up, as e to negative 4 cosine x times e to the c. E to the c, though, is a constant as well, so they write it with the c out in front. So this c that comes out in front is different than e to the c, but we can rewrite it like this as well. So if you wrote it like this is fine, or you might see it written like this. 61, split up. Y dy equals e to the x dx. Integrate both sides. Here we get y squared over 2. Here we get e to the x plus c. We're going to multiply both sides by 2 first. That's going to give us y squared equals 2e to the x plus c. And we want to solve for y here, but this is y squared, so we're going to take the square root. We have to be careful, though, because we have to take the positive and negative square root. So this has 2 forms of the solution, one that has a positive sign, one that has a negative sign. And then underneath 2e to the x plus c. Starting with 63, now we're going to solve differential equations, again using particular solutions, and we have to split these x's and y's up. So let's solve it first, then we're going to plug in to find what the value of c is. So we want to write this, we want to take the y squared over to the left side, so we're going to have divide by y squared. That's going to be the same as y to negative 2 dy. We could write it as 1 over y squared, but we want to use the power rule, so we're going to set it this way. And the 3x is going to stay on this side. We multiply it by dx. Now we have it ready to go. Integrate, integrate. Here we can use the power rule, so it's going to get bumped up by a power. So it's going to become y to the negative 1 divided by negative 1. On this side, it's going to be 3x, bump it up a power, squared over 2 plus c. And we want to get rid of the minus sign. So we're going to have y to negative 1 equals negative 3x squared over 2 plus c. And we have to take the reciprocal of both sides. So this c, I would like to combine with this, I think, so I can take the reciprocal. So I could multiply and divide this by 2, so I can combine it here. When I multiply it by 2, it's just going to become another constant. So 2 times c is going to still be a c. Then I can flip both sides, and I'm going to have 2 over negative 3x squared plus c. And I still need to find out what this c is. So now I'm going to plug in this guy. Plug in 2 for x, and it should come out to negative 215. So this is what our general equation is going to look like. And when I put in 2 for x, it should come out to negative 2 over 15. So this I'm going to plug in for y. Negative 2 over 15 equals 2 over negative 3. We're plugging in 2 for x here, plus c. And we want to simplify this. So that is going to leave us with 2 over 2 times 2 is 4. Times that is going to be negative 12 plus c. And if I look over here, I've got the 2's matching up on top. So basically I want negative 15 on the bottom. So c here is negative 3. So if c is negative 3, then I have negative 15 on the bottom. 2 over negative 15 is the same as negative 2 over 15. So now that means that this equation is really 2 over negative 3x squared minus 3. Now I can replace the c with the c I just found as negative 3. So here's my final answer. 65 dy dx is equal to 2e to the x minus 2e to the x minus y. And again, we're going to use that little trick. We're going to split this guy up. We're going to think of this as 2e to the x over e to the y, because we're subtracting the exponents here. I can write it as dividing e to the x divided by e to the y. And so that I can multiply this out, cross multiply it to get all the dy's and y's together and all the dx's and dx's and x's together. So we're going to have e to the y dy equals 2e to the x dx. You can integrate both sides. Here we're going to have e to the y equals 2e to the x plus c. And I'm going to take the natural log of both sides, so I get the y here by itself. So I have y equals the natural log of this thing. And now I can see what I got to plug in 2 for x, and this is what I should get. I got to for my y here. So this is going to take the plate. So here is the general solution, particular solution. Y is equal to natural log of 2e to the x plus 1. On the right side here I have natural log 2e to the, oh that should be 2 there, sorry, 2. And then I'm putting 2 in for that x. So you can see that most of the parts match up here. I have natural log 2e to the e squared. Here's 2e squared. Here it has plus 1. Here it has plus c. So what does c have to be? C has to be 1. So now I know, going back to my equation here, what the c value is. So the final solution is y equals natural log 2e to the x plus 1. Okay, 67. dy dx is equal to 1 over secant squared y. So this has a y in it. There's no x's here, so I'm just going to multiply that to the other side. I have secant squared y equal dy equals 1 dx. Integrate both sides, integrate the left here with respect to y. The integration formula for secant squared is tangent of y equals, this side is just going to be x plus c. So again, it's important as you integrate this side with the x's that you put the plus c in there right away. So now we're going to get the y by itself. We want to get rid of the tangent. So we're going to take the inverse tangent of both sides. So we have y is equal to the inverse tangent of x plus c. And now we got to figure out what the c is. So now that we have our general solution, we're going to plug 2 in for x and plug 0 in for y. So 0 equals inverse tangent of 2 plus c. To solve an equation like this for c here, I could take the tangent of both sides. So the tangent of 0 is equal to 2 plus c. The tangent of 0, though, is of course 0, and 0 is equal to 2 plus c. That means that c has to be negative 2. So now we know what c is. We can go back and plug that in. So our particular solution is going to be y equals inverse tangent of x, and then instead of plus c here, we're going to have minus 2. All right, dy dx is equal to e to the x over y squared. Separate, so we're going to have y squared dy equals e to the x dx. Integrate. This is going to become y cubed over 3 equals e to the x plus c. And we want to get the y by itself here. So we're going to multiply both sides by 3, take the cube root. Going to do 2 steps here at once. So we're going to be taking the cube root of 3e to the x plus, so 3 times that. Remember that c is going to be changing throughout, so that's still a c inside the cube root. So now we have our general solution, and probably easy to see what our particular solution is going to be because we're going to plug 2 in for that x, and this is what's going to come out. But we'll set it up here. So this is the y value, cube root of 3e squared plus 3 equals cube root of 3e. We're putting 2 in there for x plus c. So what does c have to be? C has to be the 3 because everything else is matching up. So c here is this 3. So now we know the value of c. We can go back to our equation. Y equals cube root of 3e to the x plus 3. All right, starting with 71, now we're doing something different here. We're still doing differential equations, but we're going to represent the solutions with something called a slope field. So as we've seen, differential equations typically have a lot of solutions. We found general solutions, and then if we have the right initial conditions, we can find a particular solution. A slope field is going to represent all the possible solutions. So the slope field here is basically telling us that the rate or the slope at any particular point is given by this formula. So here it's telling us that the rate or the slope is always 1. So that means that the slope is never changing. And you see these little dots here? That's where you're going to put your little slopes. So we're going to make a little slope on each of these line segments. But we have to imagine that we're only drawing a few of them, but this whole, wherever we go on here, whatever point you pick out, we could write the slope at that particular point. We're just going to fill it in for the dots here. So this one just says simply that the slope is always 1. So that means no matter where we go, we're going to draw a slope line, try to make these look like they have a slope of 1. So up 1 over 1, like a 45-degree angle, every possible place on this grid. And they're kind of spaced out, 1 space apart. So we just fill in all the slopes have a slope of 1. So it ends up looking like this. So no matter where I go on this space, we're saying that the slope is 1. Now this represents a whole bunch of equations or a whole bunch of solutions. So one might be this line, another one might be this line, another one might be this line. Okay, we're not going to draw those in, but it's just to represent that there are an infinite number of solutions to this differential equation, and they would tend to follow these slope lines or the slope field. So all the solutions here would be lines that have a slope of 1. 73 here says that the slope or the rate of change is -1 over y. So here it only depends on the y. So that means wherever we go here, it's going to be the negative reciprocal of y. So first off, I like to pick some easy places. So notice that this is sometimes going to be undefined if y is 0. So along this line, when the y value is 0, there is no slope. So you're not going to draw anything here because the slope here would be undefined. The slope here is undefined. Slope here is undefined, and so on. Now, since this only depends on y, pick another y value, like y equals 1. What would the slope be if the y value is always 1? Well, you put 1 into this formula, and it's telling you that the slope would be -1 over 1, which would be a slope of -1. So you make slopes here, all across here, with a slope of -1. What about down here? Now we're putting this, all these points along this line have a y value of -1. If we put -1 in there, what is that telling us? That tells us that -1 divided by -1 is going to be a positive 1. So the slopes here would look like positive 1. And I go a little bit further. If I go up to here, now what is the y value across here? The y value is 2 anywhere I go along these points. The slope here would be -1/2. So it's not going to be quite as steep. The slope here would be -1/2. Maybe make it like this. Not quite as steep. And likewise down here, we're putting -2 in. If I put that in, I'm going to get a slope of 1/2. So again, it's not quite as steep. Maybe it looks like this. These should all be parallel. These should all be parallel. Okay, so going across, they're all parallel. Here they all have a slope of -1. Here they all have a slope of -1/2. Here they have a slope of 1. Here they have a slope of 1/2. And again, there's nothing that we would draw here because it would be undefined. 75, this one depends on both x and y. So now we have to be a little bit more careful when we're drawing the slope field. But we want to make this kind of easy. So first off, notice that y here is in the bottom of a fraction. So that means, just like for the one above, if y is 0, it's not going to be defined. So along this line, we're not going to have any slopes to draw. And if x is 0, then we'd have 0 divided by y. That means that the slope is going to be 0. So here it's 0. Here the slope would be 0. Now we got to be careful. We don't draw anything here because the y value is also 0, so the slope would be undefined. But if I go here, think about what the x and y is. X here is 0, y is -1. If you plug them back in here, 0 divided by -1 is going to be 0. Here, x is 0, y is -2. 0 divided by -2 is still 0. So along the y-axis, we're going to draw slopes that have a slope of 0. Again, using this rule. This is telling us what the slope is at any particular x and y, and we just put in the x-coordinate and the y-coordinate to find out what the slopes are going to be. We draw these little line segments, these little slopes, to represent the field. Now let's go over to some other easy points. Like this point is 1, 1. What would the slope be at 1, 1? Well, if x is 1 and y is 1, the slope would be 1. Likewise, if x is 2 and y is 2, the slope would be 1. When x and y happen to be the same, then when we divide them, we're going to get 1. So -1 divided by -1 is also positive 1. -2 divided by -2 is positive 1. What if they're opposite of each other? Like if we go here, -1, 1. Well, then we get a slope of -1. -2, positive 2. Be a slope of -1. So along this diagonal, they're going to have slopes of -1. So once you start drawing some of these in, you should start to see some patterns. Like here we see a pattern. Here we're going to see a pattern. So let's see, what is it going to do at this point? Well, here x is 1, y is 2. So the slope here would be 1/2. So it's going to look something like that. Here, x is 2, y is 1. So there, the slope would be positive 2. Down here, x is 2, y is -1. So it would be -2. So a little bit steeper going that way. At this point, x is 1, y is -2. So that would be 1 over -2. So -1/2 should look something like that. Okay. And as you fill these guys in, you can see it's got this kind of divergent pattern. Here, x is -2, y is 1. So -2 divided by 1, that's going to have a slope of -2. Here it's going to have 1/2. So there is what it's going to look like. So that means solutions here would look like maybe like this. Okay, there's one solution. Here's another solution. Okay, the solutions would tend to follow these slope fields. Again, we're just drawing in a few of the points. Okay, 77. Here it has y divided by -x. So now x is on the bottom, so wherever x is 0, it's going to be undefined. So that means that along the vertical axis here, the y-axis, we're not going to have any slopes. And when y is 0, then we're going to have a slope of 0. So that means we could put little slopes of 0 going along here, except for this point because x is also 0 there. But there, we're going to have slopes of 0. Now when I put 1, 1 in, it's going to be a slope of -1. So it's going to look like this. If I put in -1, -2, and put the, -1, -1, put those in, it's going to come out to a -1. So it's still going to look like this. If I put in 1, -1, 1 is going on top, -1 is going to go on the bottom. So you got to put in the coordinates where they go there. The slope there would be +1. Here would be +1. Okay, so you just keep filling this in. I like to start with the zeros first, then I fill in the easy ones that have like 1s involved, and then you get, kind of the symmetry going on with the solutions generally. So this one's going to have like a rotational symmetry. And when we go to x is 2, y is 1, we're going to have -1/2. So that should look something like this. When x is 1 and y is 2, we're going to have -2. So it looks like this. And if they're both 2's, then the slope is still -1, like that. Here it's going to be the same, +1. Here it's going to be +1. Here it's going to be -1. Put in 2 and -1, and the slope here is going to be a +1/2. Here, if we put x is 1, y is -2, we're going to have a +2. So you can see that again, we have the symmetry going on. On this side, we're going to get -2 and a -1/2. And up here, we're going to get a 1/2. Just make it a little bit like that. And up here at -1, 2. 2 is going to go on top, so it's going to be a +2. So it looks like that. So there we got the slope field complete. All right, 79. Here we have the slope is equal to x times y. So this is probably one of the easier ones because now we're taking the product. So that means that anytime x is 0, this whole thing is going to be 0. So when does that happen? X is 0 along this line. All the slopes here are going to have a slope of 0. And when y is 0, it's also going to have a slope of 0. So here, they're all going to be 0s. And now we're going to take the product. So 1, 1, slope is 1. 2, 1, slope is 2. 2, 2, slope is 4. So it's going to get even steeper. Here it is 1, 2, slope is 2. So it should be kind of parallel to this one. On this side, a negative and a positive is going to make the slopes here negative. So this is going to be -1. -1 times 2 is -2. -2 times 1 is -2. -2. -2 times 2 is -4, so a little bit steeper there. So it's going to be kind of curved like this, and now we're going to have symmetry going from top to bottom here. So on the bottom, it's going to go negative times a negative makes it a positive. A -2 times -2 is going to be +4. On this side, it's going to be a positive times a negative, so it's going to be a negative slope, -1, -4. Here it's going to be -2. Here it's going to be, again, not looking for complete accuracy, just so you get the idea of how to make these slopes in these slope fields. So here it's -2 and -1, that's a +2. Here it's -1 and -2, +2, -1, and, +1, -2, and that's going to be -2, like that. So again, this is going to represent different equations that are going to have this as their solution. Maybe they look like this and this. 81 represents x plus y. So here we are adding. Notice that the only ones that we have anything undefined is the ones that have division. Otherwise, every point should have a little slope on it. So here, every point can be defined as just x plus y. So we're going to add the coordinates. So let's start with 0. That's easy. 0, 0 is going to be a slope of 0. Here it's 1, 0, so it's going to be a slope of 1. Here it is 2, 0, so that's going to be a slope of 2. So a little bit steeper, going this way. -1, 0 is going to be a slope of -1. And then this is -2, 0, slope of -2, a little bit steeper. Then we go down here. Let's go along the y-axis. So now x is 0. So here it's going to have a slope of 1. Here it's going to have a slope of 2. Here it's going to have a slope of -1. Here it's going to have a slope of -2. 1, 1. 1, -1, slope of 0. So now maybe the easiest one is to pick the opposites. And over here it's -1, 1. So that's going to look like that with a slope of 0. 2, -2, that's going to have a slope of 0. -2, 2, it's going to have a slope of 0. So notice I kind of skip around and I pick out the ones that are going to be easier to fill in. Like if I notice that I have x plus y, that means that the ones that are opposite are going to have a slope of 0. And now 1, 1 is going to have a slope of 2. 2, 2 is going to be even steeper, slope of 4. 2, 1, maybe a slope of 3. Here it's 1, 2, that's a slope of 3. Here it's 1, negative 2, that's going to be a slope of negative 1. So it should look parallel to that one. Here it's 2, negative 1, so that would have a slope of 1. Over here, negative 1, slope of negative 2, negative 1, negative 2. It's going to be steeper, negative 3, negative 2, and negative 1, slope of negative 3, negative 2, slope of negative 4. Over here, negative 2, negative 1, slope of negative 1, negative 2, negative 1, and 2 is going to be a slope of 1. So this one, a little bit tedious, but you get the idea. We got these lines going here, and this is what the slope field is going to look like. Okay, starting with number 83. Here you're given the slope field, and you have to pick the differential equation that it represents, or that's represented by it. So it's easier if you're looking at the PDF, which is going to have the little slopes here in blue. So I can barely see it, but if you look on the x-axis here, you should be able to see little blue marks here, 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 and here. That tells us that when y is 0, this whole thing is going to be 0. Okay, we want to keep that in mind. Notice that there are no markings along the y-axis. So that means when x is 0, that is going to be undefined. So when one of them is undefined, that's a hint that it's probably one of the division ones. Okay, so it's probably not this guy or this guy, because if x was 0 or y was 0, then we would have, zero lines here. So right now I got it narrowed down to A, B, or D. But which way is it undefined? It's undefined when x is 0. So that means the x has to be on the bottom. So now I got it narrowed down to either A or B. And now pick a point, such as this point. And this point here is 1, 1. And what does it tell us that the slope is at 1, 1? It says that the slope is going to be a negative. Looks like it's a negative 1 here. So if I put 1, 1 into this guy, it's not going to come out to negative. But here, it would come out to negative 1. Well, it looks like A is not going to work. But if you want to double check, pick another point. Maybe pick 1, negative 1. If I put 1, negative 1 in here, negative 1 would go on top, 1 would go on the bottom, and then it's going to come out to a positive slope. So it looks like B here is the best choice. So that's how you're going to do the back of these and finish up the slope fields. Try one more, but I think it's a good practice because this is going to be on your quiz and test. So we'll do one more here, 85. Again, if you look at the PDF, it should make it easier to see where the little blue lines are. There's some that are hiding here on the x-axis again, and there are none on the y-axis. So that's probably a hint that it has to be something that has over x. So you can see that we get it narrowed down to either B or E. And, well, if we take a point here, 1, 1, it has a positive slope. So if I put 1, 1 into this, it would be a negative slope. So the best answer here has to be E. If I was doing 86, notice here that along the y-axis, when x is 0, they all come out to zeros. And it looks like they come out to zeros here as well along the x-axis. So there are little blue lines here as well. So it's 0 across the x-axis, it's 0 across the y-axis. That makes me think that it's probably a product, x times y, maybe with a negative sign. It's not a division one, so if it was dividing by x or dividing by y, then one of these axes would have nothing on it. The slope would be undefined. So my best guess is probably E, but pick out a point here. So here it's 1, 1. If I put 1, 1 into this guy, it's saying that the slope is negative. 1 times negative 1 would be a negative slope. So E here is the best choice for 86. So that's how you do these at the end with the multiple choice. See if you can figure out the rest of these. All right, hopefully that helps, and we'll see you next time. Bye!